Hi everyone, now we are going to discuss about variation autoencoders, commonly known as VAEs. So VAEs are one of the most popular deep learning models used for generative AI. Unlike traditional autoencoders that only compress and reconstruct data, so VAEs learn the underlying probability distribution of the data, enabling them to generate completely new samples. So in this presentation, we will learn how a VAEs work, its architecture, training process, algorithm, and compare it with a traditional autoencoder. Building a variation autoencoder. A variation autoencoder is an advanced version of an autoencoder. Instead of learning a fixed compressed representation, it learns a probability distribution of the latent features. So this provides three important advantages. It is a generative extension of an autoencoder. It learns probability distributions instead of fixed values. It can generate new data samples similar to the training data. So because of these properties, VAEs are widely used for image generation, phase synthesis, anomaly detection, and medical imaging. Steps to build a VAE. The first component of a VAE is the encoder network. The encoder receives the input data and processes it through multiple neural network layers. Unlike a normal autoencoder, the encoder produces two outputs, mean and standard deviation. So mean, which represents the center of the distribution, standard deviation, which represents the spread of the distribution. So these two properties define a probability distribution rather than a single latent vector. Next comes the reparameterization trick, which is one of the most important concepts in VAE. Instead of directly sampling the latent vector, VAE uses the equation, that is Z equal to mu plus sigma into epsilon, where epsilon is randomly sampled from a standard normal distribution. So this technique allows gradient values to flow during backpropagation, making the model trainable using gradient descendant. So decoder networks, the sample latent vector Z is then passed to the decoder network. The decoder attempts to reconstruct the original input from the latent representation. The objective is to produce an output that is as close as possible to the original input. If the reconstruction is accurate, the decoder has successfully learned meaningful features. Loss function. Training a VAE requires two loss functions. The first is reconstruction loss, which measures how closely the reconstructed output matches the original input. The second is KL divergence loss, which forces the latent variables to follow a standard normal distribution. The total loss is calculated as total loss equal to reconstruction loss plus KL divergence loss. Together, these two losses ensure both accurate reconstruction and a smooth latent space suitable for generating new samples. The training process of a VAE follows these steps. First, the input is passed into the encoder. The encoder computes the mean and standard deviation. A latent vector is sampled using the reparameterization trick. The decoder reconstructs the input. The total loss is computed. Using backpropagation, the network weights are updated. So this process is repeated for multiple echoes until the model converges. The VAE training algorithm can be summarized as follows. For every input sample, first encode the input to obtain mu and sigma. Then the sample sigma from a standard normal distribution. Compute the latent vector using the reparameterization equation. Decode the latent vector to reconstruct the input. Calculate the total loss. Finally, update the network weights using gradient descent. This sequence is repeated until the model learns an optimal latent representation. So, encoder focuses only on feature learning and reconstruction. VAE focus on both reconstruction and data generation. Autoencoders use fixed latent vectors, whereas VAEs learn probability distributions. And autoencoders cannot generate new data efficiently, but VAEs can generate realistic new samples. And although VAEs are more computation complex, they are much more powerful for generative AI applications. The main difference is very simple. An autoencoder learns a compressed representation of existing data. A VAE learns a probability distribution from which completely new data can be generated. So this makes VAEs one of the fundamental models used in modern generative AI. So the concept presented here is based on the textbook. Thank you for your attention.